Welcome to The Explainer. Today, we are jumping right into a really core concept in natural language processing, the Word2Vec CBOW model. You've probably heard of it. It's basically one of the key ways we taught machines to actually understand language.
All right, so I've been in the data world for a while now, but I'm really trying to get my head around this whole machine learning language thing. I keep hearing about Word2Vec, and specifically the CBOW model. Can you just kind of walk me through it?
You got it. So, at its heart, the continuous bag of words, or CBOW, is actually super intuitive. It all comes down to that old saying, right? You can know a word by the company it keeps. That's literally what the model does. It looks at all the words around a blank space and tries to predict the one that's missing. So take a look at this. It's a perfect example. The model gets a bunch of context words: machines, can, recognize, objects. Its one and only job is to guess the word that should be right there in the middle. In this case, it's now. And that's where the bag of words name comes from. The model doesn't really care about the grammar or the order. It just throws all those context words into a conceptual bag and uses them to make its prediction.
Okay, that makes a lot of sense. But I've also heard about skipgram. How is that different from what we're talking about with CBOW?
Great question. They're basically two sides of the same coin. They're just inverses of each other. So, like we just saw, CBOW looks at the context, the quick fox, to guess the middle word, brown. Skipgram does the exact opposite. It starts with the word brown and tries to predict the context words around it, like the, quick, and fox. So yeah, two different paths to get to the same goal, learning what words mean based on where they show up.
Right, I get it. But hang on. When you're talking about a vocabulary with, hundreds of thousands of words, training a neural net to do this sounds insanely slow. It seems like it would take forever. How is this even practical?
That is the critical question for sure. You've hit on the main bottleneck. For every single prediction, the model would technically have to calculate a probability score for every single word in the entire vocabulary. Imagine you have 100,000 words. That's a massive, massive calculation for just one training step. It's just not feasible. But luckily, there are a couple of really clever tricks to get around this. And those two tricks are called subsampling and negative sampling. They both attack the efficiency problem, just from slightly different angles. Let's break them down one by one. Okay, so first up is subsampling. Think about it. In any language, words like the, is, or a show up all the time, but they don't really give us a lot of unique context. Subsampling basically says, hey, we've seen enough of these. It randomly throws out some of these super common words during training. This does two things. One, it massively speeds up training, and two, it actually helps the model learn better representations for the rarer, more important words. Now, negative sampling is, you could argue, even more powerful. Instead of making the model play this impossible multiple choice game, pick the right word out of 100,000, we totally reframe the problem. We give it the context, the correct word, and then just a few randomly chosen wrong words. We call these the negative samples. Then the task becomes way simpler. It's just a series of yes-no questions. Is this the right word? Yes. Is this the right word? No. This takes a giant calculation and shrinks it down to something super manageable. Okay, that makes a lot of sense now. The optimizations are clever. But what's the actual payoff? What do we get at the end of all this training that's so special? The payoff is huge. What we get are called word embeddings, which are basically dense numerical vectors for each word. And since you know databases, think of it like this. The old way, something like one-hot encoding, is like having a giant table with 100,000 columns, one for every word. And for any given word, all those columns are zero except for one. It's incredibly sparse and inefficient. Word embeddings are the complete opposite. They're like a compact, smart lookup table. Instead of 100,000 empty columns, you might have just 300 columns that are packed with rich, meaningful information about how that word relates to all the others. And here's where it gets really cool. Because these vectors actually capture meaning, you can literally do math with them. This is the classic example that blows everyone's mind. If you take the vector for France, subtract the vector for Paris, and then add the vector for Rome, you get a result that is incredibly close to the vector for Italy. It's wild. The model figured out the abstract relationship between a country and its capital, all on its own, just by reading text. So let's bring it all together. The key takeaway here is that the Word2Vec CBOW model is this incredibly efficient method for creating these dense lookup tables for words. It captures their actual meaning just by predicting a word from its context. And this ability to turn language into meaningful numbers, it's not just a neat trick. It is a fundamental building block of so much of the modern AI we use every single day.
And honestly, we're just scratching the surface here. It really makes you think, right? As our machines get better and better at grasping these deep relationships between words, what new kinds of conversations should we even be having with them? What does that future look like?
Hope you found this breakdown helpful. If you want more deep dives just like this one, you know what to do. Like, share, and subscribe. It really helps us out. Thanks for tuning in.